Okay, here's another data set for us to play around with. These show you're dropping a rock or some object and it falls a certain distance and you clock how long it takes to hit the ground. So, short distance takes a short amount of time, long distance takes longer. Nothing too surprising. Let's see if we can graph this and come up with a slope for it or a formula for it. We have fall distances that go from up to 16 meters. So here we need something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 meters. That should be okay. Our fall times only go up to about 2 seconds, so we could do like 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, 1 whole second, 1.1, 1.2, 1.3, 1.4, 1.5, 0.6, 0.7, 0.8, 0.9, and 2 seconds up there. So if we graph this data, we have 2 meters. A 2-meter drop takes 0.6 of a second. A 5-meter drop takes 1 second. A 10-meter drop takes 1.4 seconds. And a 16-meter drop takes 1.8 seconds. Now, if you go to draw a straight line through those, they don't exactly make a straight line, and that's a problem. If they aren't a straight line, that means we can't exactly say that they're y equals mx. In other words, let me use the right letters for this. Instead of y equals mx, let me say, we can't say that time is just m times distance. We just tried that and it didn't work. This assumes that they make a straight line, and the graph is telling us that isn't the case. So when this happens, and it happens a lot, it means there may be a relationship, but it isn't a straight line relationship. It's something else. And now we get to figure out what the something else is. You remember your curve shapes from math? Let's look at a few. When you have y equals mx, just a straight line, you get a linear graph. We've been seeing those. We've been enjoying those in our examples so far. But here's some other things that can happen. You can have y equals mx squared, which looks like a parabola. It gives you a U shape like this. There are cubic relationships where you have y equals mx cubed. They look like an S or a lightning bolt. They do a shape like that. You can have inverse relationships like y equals m times 1 over x, where when x gets bigger, y gets smaller. And those give you what's called a hyperbolic curve, where you get a swoop like this. And sometimes you get another swoop over here if x can be negative. But it's that kind of thing where as x gets bigger and bigger, y decreases quickly at first and then slower later on. That's an inverse relationship or a reciprocal relationship. There's also inverse square relationships where you have y equals m times not just 1 over x, but 1 over x squared. Those come up with electrical forces and gravitational forces. They give you a curve that also has this downward swoop, but it's positive on both sides because of the squaring thing. These can be tricky to tell apart. The 1 over x and the 1 over x squared look awfully similar, but there are ways to do it. And a last one I want to show you. Sometimes instead of a power of x, it's a root of x. You can have things like m root x. And their graphs hook sideways. They give you a shape like that. So if you plot your original thing and you don't get a straight line, the next question is, well, does it remind me of any of these other guys? And, well, the only one that seems to get flatter and flatter as it goes is this root x. So that I have a pretty good feeling about this one. But I'm going to do an incorrect guess first, just to show you how it works and to give us a little extra practice, and then we'll go over to our correct guess, and we'll see what happens there. So if you want to get these shapes down, I suggest you have these in your notes someplace for in case you have to linearize something. These are shapes that you should be able to recognize and know what formula goes with them. And I hope you have them because they're getting erased now. Okay, so we tried a linear relationship and it didn't work. Time to try something else. Let's get rid of this graph, most of it. The next example that I showed after the y equals mx was y equals mx squared. Let's try that and see if we get anything. To do this, we have to make a new table of values. And where the original one was fall distance and time, this one is talking about time and fall distance squared. So my new table is going to be fall distance squared, and then I'm still going to have fall time. So if this is distances squared, that means I have to take all these distances and square them. I'm going to take 2 meters and square it. 2 squared is 4. 5 squared is 25. 10 squared is 100. 16 squared is 256. And for the times, we're not changing anything about the times. This new formula still uses the regular times, it just uses squared distances. So these I just copy down. 0.6, 1.0, 1.4, 1.8. Now we graph this again and see what we get. These times are still okay, but my distance numbers are very different now, so I'm going to have to relabel my x-axis, unfortunately. Now that we're using distance squared, the numbers go up to 256. So, try not to take too long with this. 50, 100, 150, 200, 250. Yeah, that should be okay. So a fall distance of 4, which is hardly anything, gives us a fall distance of 0.6. 25, which is halfway through this, gives us a fall distance of 1. 100 gives us a fall distance of 1.4. These are fall distances squared, I should mention. And a 256 way over here gives us a fall distance of 1.8. What do you think? Straight line? Not really. This thing's got even more hook than it did before, so it looks like the square isn't a good guess either. No good. We started out saying maybe it's linear. Nope. Now we tried, is it a square? Nope. Got to try something else. We have not yet linearized the graph because we keep not getting a straight line. And if we don't have a straight line, we can't find a slope, and the slope is what we're really trying to get out of this, so we need to linearize this, which means we need to make a better guess. Well, I said that the straight line didn't work, the square didn't work. The other options we had were cube and inverse square, or inverse square, and the square root. Let's try the square root and see what we get from that. So now we're doing t equals m square root d. Right? It's always the normal t, and then we're just trying different stuff on our d to see if we can get something that comes out to a straight line. We get to make a new table of values now, which is going to be the square root of our distance versus our time. So now we get to square root all these numbers. The square root of 2 is 1.4. The square root of 5 is 2.2 something. The square root of 10 is, it's 3 point something, but I forget, I have to work it out. 3.2. And the square root of 16 is exactly 4. The times don't change, because in this formula the times aren't changed. We still use 0.6, 1.0, 1.4, 1.8, and now we get to do another graph. Because the times haven't changed, I can still use this same y-axis, but we get to rework our x-axis again. The distances, or the square roots of the distances, go up to like 4, so I can go 1, 2, 3, I made those a little big, 4. All right. Okay, let's graph it and see if we have any luck. A root distance of 1.4 is like there, and that goes with a time of 0.6. Of course, when you do this, it'll be on graph paper, and your graphs will look massively nicer than mine does, but I hope this is enough to give you the idea. If our root distance is 2.2, then our fall time is 1. 3.2 goes with 1.4, and exactly 4 goes with 1.8. That's actually not too bad. That looks reasonably straight to me. If you're satisfied that that's a straight line, it means, first, we were right about this being the formula. The formula is t equals the mass times the square root, or sorry, not mass, an m times the square root of the distance. And now that we have a straight line, we can pull a slope off of it. The slope of this line is y2 minus y1 over x2 minus x1. y2 and y1 would be our times, 1.8 minus 0.6, and our x's would be 4 and 1.4. That gives us, what, 1.2 over 2.6. 0.462 would be our slope. So the equation of motion here would be something about the time is 0.462 times the square root of the distance. We knew it would be t equals some number times the root of the distance, and now we know that number is 0.462. All right, so straight line didn't work, square didn't work. We could have tried any number of other guesses that also wouldn't have given us a straight line. This is what finally gave us a straight line, and it tells us that our formula is t equals this. That's it for the actual linearizing part. If you want to stick around for another minute, let me pull back the curtain here and I'll show you where this number actually came from, because I cooked this before I started the video. I started out with a formula that says distance equals 1/2 at squared, because that's what you use when you drop something. And if you drop something, this a is 9.81. So we get distance equals 1/2 of 9.81 t squared. Half of 9.81 is 4.905. And then, because this formula is supposed to be t equals, I had to take this and solve it for t. So to do that, I divided by 4.905 on both sides. Here I went 1 over 4.905. Those canceled. And I got 1 divided by 4.905 is 0.204. So now we have 0.204d equals t squared. And then, to get t alone, I square rooted both sides. And on the left side, I square rooted these separately. And you get t, here you get root d. And if you do the square root of 0.204, you get, well, when I just did it, I got 0.452, and that's because there was a little bit of round-off error in the numbers that I was putting in the table of values. So when we worked this out, we got 0.462, because not very high precision. When I do it this time, I get 0.452, but you can see that this is how I cooked the numbers that went into the table of values, and then when we pull that number out, we get pretty much the same thing. We're off by a couple percent because of round-off error, but there is real physics behind this, and even if you don't know what it is, you can pull the correct numbers out by doing this linearizing stuff. So one more example, and then hopefully you'll be comfortable enough to try this on your own. And if you're feeling wobbly, the instructor is always there.